probability values which can be used in pre-existing SMT models for better results. So I'll start with the model. The Okay, so now our model can the main function of our model is to generate a sequence of values or symbols from pre-existing values. Yeah, from pre-existing values like these, we can generate a sequence y, and based on this function, our model can work in two ways. Like we can use them uh, to generate a target sequence, or we can use them to generate like uh, generate a score for each phrase pair in the table. So now in this paper, we will be only using a model for that phrase pair generation, score generation, because this phrase pair score generation can be used sequentially in the SMT system to generate the best results. And why we cannot, we'll be using that over like the single target sequence generation that I'll also discuss. So according to like for model, our like encoder is a simple RNN model which takes in a sequence of values or symbols xi and generates a hidden like value like a vector representation c. So this is the hidden state representation, and for each for each xi greater than 1, we'll be having a probability distribution uh, for probability distribution to predict the next symbol. And at each after the encoder is after the whole the probability distribution runs over the whole xi, we'll have the vector representation c. And using the C, we'll be generating another different sequence Y using the decoder. So the decoder has tries to generate Y given C, the vector representation, and the hidden cell representation for the decoder is different from the encoder, and it is somewhat like this. So this is because like input will have input like for each yi will have effects from both y of I minus 1 and also the encode output, which is the vector representation. That's the reason for the like additional term c here. And according for training, we'll be the encoder and decoder will be jointly trained, because if you are to consider a sequence, so if you are to consider a sequence, the most probable or the most similar sequences based on the training can only be considered by the log likelihood. So in order to maximize that, if we are to if, in order to maximize the likelihood, if we can, we are only considering yi, we should be using values like log p theta y n by c. And we already know that the probability of C is also the probability of the like the efficiency or the log likelihood of C is will can be represented as p theta of C divided by x. And since C is a representation, a vector representation of xi. So in that consideration, appending or considering both the C vector representation and also the y, we'll have to generate a log likelihood equation like this. And according to the equation, we can understand that the encode or the C vector generation and the Y generation should be equally trained, like parallelly trained. Okay, and then the novelty in this paper can be considered from this like novel hidden part. So hidden unit. So in here the we have two additions to the hidden unit. One is an R reset gate, and reset gate uh, determines how much of like whether the previous hidden state value is to be ignored. And like this can be useful, because if we are considering context length or shorter context length, the reset gate value can be approximately equal to 0. And we can see that if this value is approximately equal to 0, we will not have like effects from the previous hidden state. So these so that is the use of a reset gate. Like it depends where it determines whether the previous hidden state or the previous context should be added to the next symbol. And as for Z gate, the update gate or the Z gate, will the Z gate determines how much of the information will be like carried over to the next hidden state. So if we have a hidden state, we are calculated the hidden state H bar at each stage, and the Z gate determines the how much value or whether the past Z gate value should go to the next cell or whether it should not. So that's the value of Z. And with these two additions, the final like hidden representation of a network would be something like this. And our t state will have hg of t, and this hd of t is normally calculated as I discussed in the previous slides, like here. The only addition would be h bar of t, which is a term which includes both the effects of r and z, from z. And also here in the equation we can see the dot product of H and R. So these determines the whether like the effect of R and Z should be included and how to include them. And going so now, like I said, the target. Let me explain why. Okay. Let me explain with results on the paper itself. So this is from one of the outputs from the RNN model, RNN decoder. So we can see that the number of outputs are in multiples. The RNN encoder model does not give a clear translation of the model. So that's why clear exact target phrase for each of the single phases. So that is one of the main reasons why we'll be for which we'll be using the this RNN encoder model with the stat SMT or the statistical model. So in statistical model, each target translation app from a source sentence E, we'll be considering that sentence or that target phrase which has the maximum log p value. And so for each sentence, the sentence or the phrase, the translation phrase which has the maximum log of this value will be considered as output. And our RNN encoder model can be used to calculate the PF of E value, because our PF of E values, and we'll go into the result, compare the results with this. And for these are the parameters of the model that has been suggested. The h bar that we have finally considered is a hyperbolic function, and these are the other parameters with gradient descent values and all. So the baseline model is the CSLM model, which the SMT model, which uses log PF for phi values. And we can see that the testing and development values for this, and the R encoder has slightly increased values when considered to the test values. But the most important thing is the model, SMT model plus the encoder decoder model can be seen to provide better results when combined. So the reasons for that I'll explain right now. And we can also see a word penalty. So what word penalty is, that also I'll explain. So the thing is, the model, basically, I'll explain from the quick for this portion. So the model has been consider this sentence. So the model, the translation model basically works on the basis of frequency. So each of these words has been formulated based on the existence of the frequency and counts, and the log value depends on that. While the RNN model, due to the presentation of each cell and symbolic representation, we'll have a continuous phase representation for each of the output, and the C which we talked about is also a continuous phase representation. So we'll be having the linguistic representation, or we'll the RNN encoder model it has been able to capture the semantic and syntactic representation of each sentences. So that's why the when combined with the frequency values and with the semantic values, these models together has been given proven to give very good values. And the one of the most important things is in these are for long frequent source phrases, and these are for rare frequent sources. But even if the frequency of the words are higher or lower, the translations provided by the combined model has been seen to be quite good. And now this is basically because our model not only considers the frequency, it can be said that the combined model includes much more in-depth values than just RNN. And this also proves that our model is not correlated. The SMT model and RNN model works in separate ways, and even though they have possible similar results in some cases, like here we can see that some similar responses, but in some other cases here we can see that even though the phrases are long or the frequency is high, the model has given different results. And this is basically because of the basic theory that our model uses in semantics relation. However, the translation model has a frequency related representation. That's why these differences occur. And that's these differences in theoretical aspect is also the reason they have similar results in some cases. So we can say that they have they can cover the most edge cases of results. And like I said, now the word penalty. So now the most common thing that we can have confusion will be the word, what if the model comes across a word that it has not ever seen. So in testing, if so for that we have added a method in last model. We add The paper has considered of adding a method to penalizing unknown words in the z z representation. I'll show the okay, in the blue score representation they'll have added the Z presentation, they will be using a log likelihood of unknown words and penalizing those. So even with those in the development, we have seen an increase, but in testing, the results were lower than we expected. So word penalty, the method of approaching low word penalty, or unknown words with a word penalty, was proven shown to be not good enough in this paper, but we can still use the CSMT plus RNN method. And these are the cells that I just discussed. The model that I have to explained generates a continuous representation, and therefore capture semantic result. I'll present the outputs that the paper has discussed. And now, so the scores, the blue scores of the model has been compared to be has been shown to be better than that just by an SMT model. And we have seen that the linguistic relation in the phrase pairs has been detected by the proposed model. So, for, for continuous phrase representation, so this is the continuous phrase representation that the model has came upon. So in each area, from in this particular space reference, we can see that each of the colored area that has a similar semantic meaning. For example, here the blue colored area represents the countries like this Israel and kingdom or something. So these represents words with some with a particular semantic relationship, and these are all numbers as represented by the B. So this space representation at each point in the space representation has an like uh, words clustered together based on their commonness or similarity in their semantic meanings. And now that's for just words, and we have the same relationship generated for uh, phrases, short length phrases. And we can see the most visible or not confusing image here is the last one. Here we can see that These words are representing something of a time span. So we can say that the model, and here also the company is like with more than one line. So in general, we can see that the continuous face representation has been presented quite well by the model, and the linguistic relationship between the words has also been captured. So I think that's it.